So. Okay. So are there any questions about the homework assignment? Going once, going twice. Okay, I guess there are no questions about the homework assignment. So what we'll do today is we're going to move forward and we'll talk about local variables and well, we talked about parameters already. So what we'll do is to talk about local variables. Okay. All right. So in order to talk about local variables, it is probably a good idea to talk about recursion a little bit, because recursion relies on each invocation of a subroutine to have its own local variables. Okay. So let's go ahead and write a kind of clumsy recursive subroutine first, and then we'll go ahead and implement it in assembly as well, so that we can take a look at how things are actually done. Okay, and we'll just do the usual stuff, which is factorial. Not sure whether this font is. You guys okay? Yeah. Okay. So let's do. I'm going to bump up the font size a little bit, just so that it's a little bit easier to read, because some of you are pretty far away from the screen. Okay, I think that should be okay. All right, so we'll go ahead and write a subroutine, which is factorial recursively, and factorial the recursive version of factorial is actually not very hard to do, and it does not even need to use local variables. But I'm just going to make a version that requires the use of a local variable, just so that I can demonstrate what it is. So we'll have a local variable called R for result, and the usual stuff goes here. If n is greater than 1, we'll do it recursively. Otherwise, we can stop the recursion and specify R is 1 in here, and then over here we can say R is n times, well, okay, we can do it in 2 steps, okay, just so that I can find a use of the local variable. Oh, this is going to do multiplication. It's okay. I'll just talk about the multiply instruction when the time comes. Okay, it's going to be okay. So f of n minus 1. There we go. And then at the very end, we just return an R, and that's one clumsy and longer way to implement factorial, but use a recursion. Okay? Most people use multiple returns in the conditional statement with something like this, which is okay. Just personally, I do not like to have. I don't like returns inside a conditional statement or loop. Are there any questions about this particular subroutine in C? No questions about this in C? It's all good? Okay. So here's a trick question. Just looking at this code, how many local variables, or how many R's are there with this subroutine? The correct answer is we don't know, okay? Because we do not actually have R. R does not exist as a local variable. R does not exist until the subroutine is invoked. And when it is invoked, every invocation has its own R, okay? So that is something that we have to keep in mind, is when you use local variables in C, C++, and most programming languages, they do not exist until the subroutine is invoked. And when it is invoked, you have one local variable per invocation. Now, you might say, but most subroutines are not recursive. Is that really important? And the answer is yes, it is still important, especially in a multi-threading type of process. Okay. So what we'll do today is we'll test run this program first, and we'll do the usual thing. We're not even going to rely on printf or anything like that. We'll go ahead and calculate the factorial of, I don't know, that's probably not before, okay? And return to 0. So the compiler will definitely complain about x is initialized but not used, because inside the main subroutine, x is assigned a value, but then x is never used for anything that is useful. But that's okay, it's not the main part of this program. GCC, I'm going to shortcut the whole thing and not use a makefile, at least not for the time being. So dash G to include debug information, dash O to specify the output, which I can just call factorial. And then the source code is factorial.c. Compile the whole thing, gdb factorial. And we can now put a breakpoint in the program. So what I'll do is I'm going to put a breakpoint in R. So let's go ahead and list one from line 5. And put a breakpoint on line, I don't know, let's put a breakpoint on line 5. So at the very entry point of the entire subroutine F, I'm going to put a breakpoint there. Every time I call itself, every time F is called, it will stop, so I have a chance to look at stuff on the stack. Are there any questions about this program for now? Does anyone not have any exposure to recursion from previous classes? Okay, very good. So run the program. This is the first invocation. In the first invocation, what do you think n should be? From main, I called f with a parameter of 4. So the first invocation would have n equal to 4, and it is actually spelled out here. Okay. Well, okay, that's fine. With single step, and now here is the recursion. So when we do a single step here, it will call the second time, and you can see that n equals to 3 at this point. And if we single step a few more times, n equals to 2, and at this point n equals to 1. Okay, so if I ask you a trick question, which is what is parameter n, what would be the answer?
Which n?
Very good. How many n's are there?
So far. 3.
There are 4.
Yeah.
Yep. There are 4 n's, and that's why it's a trick question, because when I ask what is the value of n, the correct answer is what you said. Which n are we talking about? Okay. Now, if you do a backtrack right now, it will show pretty clearly that we have several invocations of f. Okay. It shows that at frame 0, it's called frame 0 because this is where we are. That's why it's called frame 0. Frame 1 is the one before, frame 2 is 2 before, and so on. And you can definitely see that f is invoked up to this point 4 times. And each time f is invoked, it has its own local variable r as well as its parameter n. Is that okay so far? Now this is a very, very important concept because I have seen a lot of people understanding, quote unquote, the basic mechanism of subroutines, but once it gets to recursion, they do not understand recursion. Well, to me, that tells me that they do not understand something about subroutines because a recursive call is no different from a non-recursive call. The mechanism is exactly the same. Okay? So why is it that some people do not understand recursion when they can understand all of the other types of subroutines? It has mostly to do with local variables and parameters on a per invocation basis. Okay. So now with BT it's nice because I can now put myself back into, let's say, frame 2 and find out what is R in frame 2 instead of the current frame. So I can now use the frame command and say, I want to switch back onto frame 2. And then I can print the R of frame 2. What do you think R should be in frame 2? It should be the same as n. So that would be, should be 3. It is 3. Okay? So, and if I switch to a different frame, in other words, if I switch to frame 1 and print R, what do you think that R should be? And that it is. So this is pretty clear evidence that we have, one for each invocation, there is a whole set of parameters and local variables. Now, yep, go ahead.
Each of those parameters is stored in the stack?
That is correct. Well, we already know that the parameters are on the stack because we push the parameters on the stack and then we call a subroutine. So whether the subroutine is where you are in, meaning it's recursive or not, doesn't matter. You keep pushing more parameters on the stack and call the subroutine. Is that okay?
Yeah.
But in addition to knowing the parameters are on the stack, now we have a pretty good evidence that local variables are on the stack as well. Because they have the same type of lifespan. When you enter a subroutine, the local variables are now alive. When you exit from a subroutine, the variables are gone. Just like the parameters. Is that okay? Yep.
Are static variables saved?
Static local variables are different. Static local variables are basically quote unquote global, but they, in terms of lifespan, they are the same as global variables, which means they start to exist at the very beginning of the entire program, and they will only cease to exist when the program exits. However, unlike global variables, static local variables have a scope of just the subroutine that is containing the definition. In other words, it's always around, but nobody can see it except for the subroutine that includes the declaration of the static local variable. There are very, very few uses of static local variables. In most programs that you will be writing, in a college, setting, there should be almost no situation where a static local variable is really needed. Yep.
If for some reason you use a static local variable in a recursive function, would it keep making static local variables? Or
No, it would not. It would be all the invocations would be sharing. We'll be using the same static local variable, which is sometimes useful, okay? Maybe that is intentional so that you can communicate something from one invocation to the next invocation. But most of the time, if you have something to communicate from one invocation to the next, you would let the parameters do that trick and not utilize a static local variable. It might be more efficient, but from the analysis point of view, it makes your program more difficult to analyze. That's a very, very good point, okay? Because there are static local variables in C and C++, and they are not on the stack. But without spelling out static, S-T-A-T-I-C, in front of a local variable declaration, the default is auto, which means it is on the stack. Okay, very good. Are there any questions at this point about the demonstration of this program? Any questions about backtrack, the command in GDB, or frame, which is also a command in GDB? No questions? Okay. So the next time you have to write or debug a recursive subroutine, remember this command, these two commands, backtrack and frame, because it can be helpful. Because otherwise, if you do not use backtrack, you can only see where you are at this point, but what about all the previous invocations of the same subroutine? Well, one, you don't even know how many there are, okay? You do not know the parameters of all the previous ones that led your way here. And you cannot use frame to go back to a previous one and say, okay, I need to look at a local variable, but not of the current frame, but of a few frames back. So these two commands give you, an additional abilities to debug a recursive subroutine. And for those of you who have not taken data structure cisp310 yet, okay, you will probably find these useful when you get into cisp310. And for those of you who have already taken cisp310, do you recall any circumstances where backtrack or frame might have been useful when you're debugging the program? Maybe.
Definitely, recursive is everywhere. Data structures.
Yep. Because just knowing where you are, at a certain point, is not necessarily enough. Does not necessarily give you enough information to debug a program. All right. So do you guys want me to finish this program or not?
Sure.
Okay, so we'll go ahead and single step. This time it goes to the else portion. R is 1, return R. So we are now returning from the 4th invocation back to the 3rd invocation. And to show that, we can do a backtrack at this point. Execute a return, execute the actual, execute a return statement which specifies the return value, and then the closed curly brace would actually return to the previous invocation. Now when we do a BT, it only has 3 frames of F left. Okay, and we'll do the multiplication, and actually it just finished the multiplication. Now we get to the end and do a return. Now we are back to the second.
Huh?
What? Well, we just got back, so we are now back onto the second invocation, and this is before the multiplication is done. So, well, I guess it is after the multiplication is done in the second frame. And then single step to return, and back here, it should be 24 now. But these are all different R's. Now, the other reason why you can confirm that these are all different R's, let me just run the program from the beginning again. The other reason why you know these are all different R's, let me just go all the way to the last invocation, which is now. You can say, print where is R, okay? What is the address of R? Okay, this one ends with 8cc, okay? Go to a different frame, frame 1, and then you say, hey, where is R? See how this one is different? If you go to frame 2, just using this particular, just seeing what we are seeing right now, what do you think is the address of R at this point? In the last frame, which is the lowest frame, it has an address of CC. In the second last frame, it has an address of FC. So at this point, what do you think would be the address of R? It's going to be, okay, from C to F, how many bytes are we talking about? We have 24 bytes. No, excuse me, 48 bytes. Okay, what is F minus C? What is 15 minus 12? 3, right? But it's the second last or second least significant digit in hexadecimal, which is base 16. What is 3 times 16? 48. So each frame is apparently taking up 48 bytes. So that means, the address of R at this point should be FC plus 30 in hexadecimal. That will turn it into 92C. So the least significant 3 digits of the address should be 92C if my arithmetic is not wrong. And then the next one is going to be 95C because we are bumping it up by 30 in hexadecimal for each frame, which also tells you that each frame is consuming 48 bytes on the stack, which is really quite a bit, okay? That's a lot of bytes for a tiny little subroutine that only has one parameter and one local variable. Is that okay so far? Any questions? No questions? Okay, let me ask you another question then. Knowing where R is, okay, which is a local variable, can anyone kind of guesstimate, okay, where is the parameter? If I were to print ampersand n at this point, can you, kind of guesstimate, where n is, at this point? It's the end of the same frame, okay? So it's the same frame. The question is, what do you think is between the parameter n and the local variable R?
Memory address to return.
Okay, that's a good starting point. Okay. So what I'm going to do now is to use mousepad to help display, so that this part will also be recorded in the video. Okay. So we know the stack is going to grow down, and the usual way that I display or show memory is up is higher memory and low is lower memory. Okay. So we know the parameter is always the first thing to push by the caller, and that's why it always has the highest address. So we'll have, in this particular case, we have parameter n at the top portion, and then the caller will call the callee, which means the return address is the next item to be quote-unquote pushed, except it's not really pushed, it is done by the call instruction. And then after that, does anyone remember the quote-unquote typical entry code of a subroutine? What do we do the first thing we get into a subroutine? Push EBP. Okay, so that means on the stack we have the quote-unquote old EBP. And then after that, the stack is free for general use. Wait, but we have a local variable. This is where the local variable goes. Okay, so in this case we have local variable R, and it usually goes there. Okay, So according to this theory, what do you think? Where do you think is n? Knowing where r is already, n should be how many bytes away from it? 12 bytes away. So that would be, if we look at our code, our address here, it will be 2c plus c, which will make it a 3, 8. So let's see if it is if it ends with 3, 8, and it does not. It is a 4c. So that means it's actually putting something in between the local variable and the parameter. This is actually, yep, go ahead.
Can we check a stack data here, like in a chunk? Like a dump or?
We can, so we'll do an x slash, so let's see how many are we talking about here. R is the local variable, that's probably the last thing we have on the stack. So we want to go from 2c all the way to 40. And we want to divide it by 4. We know each call frame is 48 bytes.
48.
Yep. So 48 bytes means it only has 48 divided by 3 is 16. No, wait. Divided by 16, no, divided by 4 is 12. Because I want to print it in 4-byte chunks, 32-bit chunks. So 12, 32-bit thing in hexadecimal, and starting at where the ESP is. Okay, this is what we have on the stack. And you can probably recognize some of these things. There are something here that I do not know, why it's here. So let's check which frame we're in. Okay, R has a value of 3, and the stack pointer is also much lower than 2C2, because 2C is right here. This is our local variable R, but the stack pointer went all the way down here. N is over at 40, which is not even included, it's not even printed here. Okay, let's do one more thing. Let's make it 13. All right, so this is our parameter N. This is our local variable R. The stack pointer is pointing to this byte here. So it had pushed pushed something else on the stack, or it had pushed something else on the stack and has not reclaimed that space. Let's check with the frame pointer. Okay, so we'll go ahead and print the frame pointer and see where it is. And the frame pointer is definitely different. It is at 3.8, which is here, which kind of makes more sense because the frame pointer should always be pointing to the old EVP. Does that look like an old EVP to you? Well, but is it in the right range of address for the previous value of EVP? What is the current value of EVP? BFFF F938, right? And at the address of BFFF F938 is the address of BFFF F968.
That's 40 something away, right?
Mm-hmm. That's 40 bytes away, which is the size of one frame. 30, sorry, it's 30 bytes or 48 bytes away, which is the size of a frame.
Yeah.
So it does make sense. It is our saved frame pointer. And next to it is the address of 080483EC. Does anyone remember, where that address is located? It's not in the stack. Where is it? It's in the .text segment, okay, where the code is located. So that is our return address. What is above the return address, is 3, and that would be our parameter, the parameter N. So in this case, it had pushed something else on the stack before it actually it pushed the this is our R, because R has an address of 2C, and this is 20, 24, 28, this is 2C. So the compiler did something, and it pushed some additional stuff on the stack that I do not know exactly what it is, but it is below the frame pointer. The local variable is below the frame pointer. Yep.
Explain that how you like count 48 bits each time.
Say again?
How you like follow 48 bits each time?
Because each chunk is a 32-bit thing, so it takes up 4 bytes. In other words, when you look at this address here, this address is the address of a single byte. But which byte are we talking about? It is the least significant byte of this particular 32-bit word. It takes 32 bits or 4 bytes to move on to the next one. So we know this one is ending with 24. The address of this byte is ending with 24. This one is ending with 28. And then 8 plus 4 is C in hexadecimal. So this is actually ending with 2C as when we talk about the address. Okay? Okay, but the most important part is we kind of know where the local variable is now, because the local variable is lower, has an address that is lower than where the EBP is, or the saved EBP. Is that okay? So when you write your own subroutine, when you implement a C subroutine in assembly, you can follow the same convention. You can allocate the storage of a local variable after you push EBP. Then you can allocate some additional storage for local variables, and then you can basically then you can use the rest of the stack for whatever you need to use it for. Are there any questions? There are still something on the stack that I cannot explain. I will point out exactly which 2 items I cannot explain. This item and this item here. These 2 I cannot explain why they are on the stack.
Can you print what's at that location?
What is
If
at that location?
Yeah, depending on if it's probably not viewable to
Well, I can't.
readable for us.
Well, we can do that. It's just whether it is going to be useful or not. So we can do something like this. Well, there are several ways to do it. We can always use examine as well, and just copy and paste this code, this particular address here. And that doesn't look like a very useful address to me. That looks like it is way lower than what it needs to be. We can check this one out. And that one doesn't seem like there's a certain pattern to it, C1, CE, and the 2737. It doesn't look random to me, but yet I do not know how it is used. But we know it's somewhere on the stack, and it is in the previous call frame. But I have no idea. It's some kind of bookkeeping information, I think, but I could be wrong. So these 2 items I cannot explain on the stack, why they're there, but the most important part is the location, the relative location of the local variable R, as opposed to the location of old EBP, which is here. Okay. So let's go ahead and write this subroutine in assembly, and make sure that it does work the same way. Okay. So this would be a good time to use -O. Uppercase O means you can open up 2 files side by side. So we'll open up factorial.c, which is the C version, and f.uppercase S, which is the assembly version of function f. So let's go ahead and do it here. Dot text, which is usually not needed. Dot global f to export the label f. And this is the entry point of f. And this time I will not forget the return instruction. Last time I did, and that was embarrassing. Okay, so now I want to use labels to remember the displacement to various items in the frame. You don't have to do it like this, but this is the way I do it. Old EBP has an offset of 0 or displacement of 0 because the register EBP is always pointing to a saved version of itself on the stack. So that's why I label this place as old EBP. Save EBP would probably be a better word. The next one is return address. It is old EBP plus 4. The next one is going to be my parameter n. So n is going to be return address plus 4. And where do you think I should put local variable r? Old EBP minus 1. Okay. In other words, everything is relative to where old EBP is. So this one is going to be old EBP minus 4. The reason why it's minus 4 is not because old EBP itself is 4 bytes long. It is because R itself is 4 bytes long. Okay. All right. So now we use the typical entry point code, which is push EBP, move ESP to EBP. And then the exit code is exactly the reverse, which is move L, EBP to ESP, and pop L, EBP. And right here, I need to do something to the stack pointer. Because right now, the stack pointer and the frame pointer both are pointing to old EBP. I have not reserved any space for my local variable R just yet. Even though I have a displacement for it, it is not allocated yet. So it is important that we do the allocation at this point. There are several ways to do this. This is one way to do it. So I'm going to specify this instruction here and comment it as, allocate space for local variable R. So I'm just going to write the abbreviated version of the comment here. So we'll just kind of look at this instruction, and I just want to make sure that you guys understand that this is going to allocate 4 more bytes on the stack for my local variable R. Is that making sense to you? Okay, all right. So from here on, I can now, basically just do all the usual stuff, and I'm going to implement the exact code here using the same logic. So the first thing we need to do is to compare n, the parameter, to 1, CMPL, 1, and n %EBP. This is the base addressing mode. We talked about it in the previous class already. And J, in this case, J and G to the else label. Else goes here. And then here we have the then block. The then block starts with copying n to R. There are no way, okay, this is what I want to do. I want to copy n EBP to R EBP. Hey, that works too. This actually works because even though R is a negative number, you can specify a negative displacement to a base register. It works just as well. So you can specify a positive number like n, or you can specify a negative number like R, and both will work in this case.
Aren't they both memory? Technically memory? Aren't they both
Exactly.
memory?
That's why it's not going to work.
Yeah.
So there are several ways to get around this problem. The usual way, which is the least expensive way, is just to put it into a register and then copy the register into the destination. Because otherwise we end up with 2 operands that are both memory operands, and the compiler, the assembler, would not let us go. Okay. And then the next instruction is the recursive call. Okay, how do we do this recursive call? In terms of what do we need to do first? Tech, I think we need to talk about the multiply instruction now. Well, I know eventually we have to, but is this the right time to do it? Not quite, because we don't have the other number to multiply, right? Okay, so what do we need to do now? We need to call F again. Well, can we just say call F at this point? We're not ready for that yet because we have to push the parameter, which is n minus 1, right? Okay, so how do we push n minus 1 on the stack? Okay, from previous classes, these are the most popular mistakes. Okay, so you are benefiting from all the previous classes because you now know this is not going to work. Now, when I say this is not going to work, I simply means it is not going to work at runtime. The compiler would actually take this and do something with it and give you the wrong code, and it's going to crash. What do you think the compiler is going to do? What does n minus 1 look like as an operand? if I were to put move L n minus 1 without the dollar sign, comma EAX, percent EAX, what do you think n minus 1 is in terms of the type of operand? What addressing mode are we talking about?
Direct.
Sorry?
Direct.
Direct, as exactly. And exactly which address are we trying to access in this case? 3, exactly. And do you think location 3 in memory is where you can access, your process can access? And as a result, as a result, your program is going to give you a segmentation fault right here. Okay? So, and when people get a segmentation fault, the next thing they do is to say, that won't give me a segmentation fault. And guess what? This is still a valid operand for push L. But it's not going to do the right thing either. But what is it pushing on the stack? The value 3 on the stack. Okay? Well, sometimes n minus 1 is exactly 3, but not usually. Okay? So that's not what you want either. Fine. So what do we do now? Okay? Well, there are many ways to do this. Okay? So this is one way to do it. I can actually push n on the stack first, and then subtract 1 from what I have just pushed on the stack. Not exactly the quickest way to do things, but it is one way to do things. Because now I can say, what I really need on the stack as the parameter to the next invocation is not n, I want it to be n minus 1. How about we just tweak the location that we have just put? How about we just tweak the value that we just pushed on the stack by doing something like that? Would that work? We just push the value of my own parameter n on the stack, but the next invocation needs n minus 1. Hey, but since n is what the stack pointer is pointing to right now, subtracting 1 from where the stack pointer is pointing to will do exactly what I want to do. So this is one way to do it. Now, remember I mentioned this is not an efficient way to do it? Yep.
So later we have to change that to add 1 to a ESP again.
Say again?
So after this line, do we have to change add 1 to a ESP again
Nope.
to a set?
Because we are not changing the stack pointer, we're changing what the stack pointer is pointing to. So we are not adjusting the stack pointer, we are just changing the value pointed, or the location pointed to by the stack pointer. Okay? But this is not efficient. It's not efficient because I am actually accessing memory more than what I need to. It is much more efficient to move NEBP into EAX, subtract 1 from EAX, and then push EAX on the stack. Because in that case, I really only have 1 memory access, not counting the push instruction. In this case, I have 2 memory access, and it is unnecessary. But it is one way to do it. I just wanted to show you a combination of instructions that will accomplish what I needed to do. Once the parameter is on the stack, I call F. When it comes back, I'm going to adjust the stack pointer to reclaim the 4 bytes which are the parameters. And right now, the return value of F is in EAX. Would this be a good time to do the multiply thing? Yep, absolutely. So the multiply instruction, I'll give you the instruction first, and then we'll talk about it. The multiply instruction is mul L for multiply long, and the correct way to do it here is, if I remember correctly, I can do it this way. Okay, but this is it. This is the multiply instruction. And then most people look at this and go like, but where is the other value that we are multiplying with? Because multiplication needs 2 values. It is only specifying one of those 2. Where's the other one? It's in EAX and it's implied. Okay, so the Intel instruction set, when it comes to multiplication, it is automatically and mandatorily using EAX as one of the numbers to multiply. You can specify the other one as an operand, but EAX is quote unquote built in to the instruction itself. Are we doing okay so far with that one? Because it's kind of strange, because subtraction doesn't work this way, addition does not work this way, comparison does not work this way, but multiply does. Yep.
So it stores it into whatever you specify after mul?
No, it stores it into
EAX?
EDX and EAX. Okay, so that's the other thing about the multiply instruction that many people do not remember, is it always stores the result back into EAX and EDX. The reason why is because when you have a 32-bit number multiplying a 32-bit number, what is the potential width of the product? 64-bit, right? 64-bit long, and 64-bit won't fit into EAX. So the Intel instruction set automatically makes use of two registers, and these two are fixed as well. EDX stores the most significant 32-bit of the product, and EAX stores the least significant 32-bit of the product. Are we doing okay so far with this? So not knowing or forgetting that multiply instruction actually modifies EDX, a lot of times people get bitten by this one because they use EDX to store something, in their own algorithm, and then they run the multiply instruction, not knowing or not remembering that mul is going to change EDX, and then the program stops working because EDX is now gone. It is actually used by the multiply instruction. Yep.
Even if it doesn't result in a number bigger than 32 bits?
That is correct. If the end result is a number that can be represented in 32-bit, it will still overwrite EDX with either all zeros when the number is non-negative, or all ones in binary when the value is negative. In other words, it always overwrites EDX. And that's just the convention. That's how the instruction works. Yep.
Can you just repeat the most significant goes into what and
The most significant 32 bits go into EDX, and the least significant 32 bits go into EAX.
AX is at least. That's right. Could you?
The most significant 32 bits go into EDX, the least significant 32 bits go into EAX. Yep.
Now, if the number can be represented in 32 bits, EAX is not overwritten, correct?
It is always overwritten.
Well, EDX is and EAX.
It's always stored in EDX and EAX.
Okay.
Because the end result of the product is always 64-bit long. Yep.
So do RISC architecture use multiply?
Yes, RISC architectures most typically have a multiply instruction. It'll be pretty hard pressed to find a processor that does not have the multiply instruction. But most RISC architectures will give you will make you specify both operands. Yep. Yes, you can multiply word. I do not remember in the multiply word what registers are used. So I'm not. If I have to guess, this is just my guess based on what we have seen so far. If you do a MULW, M-U-L-W, which is multiply word, which does exist, I think it overwrites AX and DX to store a 32-bit number. Now remember, it doesn't make sense, right? Because EAX is 32-bit wide. Why not we just store everything into EDX when you multiply word? Or if you multiply byte, which I do not know whether it exists or not, it will probably store into AL and DL instead of just AX. Now the reason why why I think it would do it in this awkward way is because the x86 architecture, which is this is the 386 instruction set, but it evolves from an 8-bit processor. Okay, so everything started off as an 8-bit processor. So there's no such thing as AL because it's just register A. It is an 8-bit register. We have register B, register C, and register D. And the mul instruction back in those days probably stored the product into A and D. When it upgraded into a 16-bit processor, then we have AX and DX. And then when we upgraded yet again into 32-bit, now we have EAX and EDX. So with a 64-bit instruction set, it will probably store into, is it QAX, quad word AX, whatever the 64-bit version of register A is, and then whatever the 64-bit version of register D is, but it will still use two registers to store the result. But it has to do with the legacy code, and they cannot break legacy code. In other words, the same binary code still has to work exactly the same way, even if it's an 8-bit or 16-bit instruction. For backward compatibility, so that you can run good old DOS with your brand spanking new i7 quad-core processor.
I always do that.
Hmm?
I always run DOS in my i7.
Well, this is a good question. Yeah, go ahead.
Problem is that most operating systems now emulate DOS.
Yes.
Well, no one runs DOS because it only needs an 8-bit system you can run it on.
Yeah, but if you tell Microsoft, they have to retool their compilers and whatnot to target a new architecture, they're not going to do it.
Yeah.
Yep. Over all of these years, Microsoft has displayed a whole lot of resistance to moving on to a different architecture. So I'll just confirm this once and for all. x86.
Eventually they'll go out of business. So eventually they'll go out of business.
I don't think it will go out of business. It will become the next NetWare.
Yeah.
Is it NetWare?
Well, they're
The company that made a network operating system all back in the past.
I don't remember. But it was
Novell, no,
Yeah,
Novell.
Novell, yeah.
Yeah, it'll become the next Novell. Basically, it's still here, but it's not quite the same as before.
Well, tablets are going to eventually take over, and Microsoft isn't going to rule the tablet world. So.
Yeah, but tablets mostly use non-Intel processors.
Yeah.
So I just found the answer here. I'm not sure whether you can see it or not. I'm just-
This will eventually.
Okay, so right there, mode W is going to make use of EX and RX. That's it. It stores the result into those two. Which is kind of awkward, okay? Because when you think about it, we have EAX being a 32-bit register. Why not just put it into the 32-bit register? We can't, because we have to maintain backward binary code compatibility. That's basically what it is. All right. So getting back to our program here, that's a little bit of a digression. Back to here, what we'll do is we'll multiply R to EAX, which is already storing the return value from F. And when it's all done, guess what? It's all in EAX already. But in order for this code to follow the C code exactly, I'm going to have to put it into my local variable R, and then we branch all the way to end if. This is the else branch, and if goes here. The else branch is easy to do because all we have to do is to store a 1 into R, like so. Yep.
What happens when you exceed a 32-bit number?
Then it will just kind of wrap around.
I mean, where you become where it's stored in EAX and EDX.
It always stores the product into EAX and EDX.
Yes, but the product. So if you have a 32-bit half.
You mean from the C perspective?
From assembly.
From assembly?
Yeah.
I'm just ignoring EDX entirely.
Okay.
Which is what your C code is doing. Okay, so when you write a program like this in C, and the product of two numbers cannot be represented using 32 bits, it's truncating it. It's just throwing away all the other bits and store the least significant 32 bits, which is exactly what I'm doing here.
Okay.
I'm doing absolutely nothing with EDX. I'm not storing it, I'm not changing it. Well, I am changing it using the roll instruction, but not otherwise using it for anything else. So when I return the value, or when I specify the return value, all I really have to do is to put copy R, the local variable, into EAX, and then the rest of the code will exit correctly. Yep. So how many people think that this code may work? Okay, well, I don't have as much faith, but we'll see. I usually make some kind of mistake somewhere that breaks the program. Okay, so I'm going to modify the C code not to use the definition in the C program itself. I could have renamed the subroutine against. Get out of both programs, and we'll just do I'm just going to be lazy and recompile both because both needs to be recompiled anyway. So dash wall, dash C, oh, dash, we can do a dash O here. Dash G, okay, factorial, dash G. And then the source file name, factorial.c, and f dot uppercase s. And it complains about x is set but not used, but that's absolutely okay. And we'll gdb factorial. Let's put a breakpoint at in function f, just like before, but this time it's in assembly. So run the program. Now we are in the subroutine in f, and you can see it's not really setting a breakpoint at the very beginning because it's using the C convention, so it knows that the push EBP is not a part of the instruction that it has to stop at. So we'll just go ahead and continue, and one more time. This is the last invocation. Okay, this is the last invocation, and we'll do a BT first. Okay, how many people think the BT will fail entirely at this point because we have been writing this particular subroutine in assembly and not in C? It will fail a little bit. Okay, it will fail to identify the parameters right away. Okay, that part it will fail because we did not really provide a prototype for GDB to understand. So when you do a BT, it actually does a fairly good job. It understands that this is the fourth invocation of F, which is actually pretty good. So now the question is, how does it do it? How does backtrack, do something like this? Understanding that, hey, before this one, it's called from F, and on line 18 too. Do you think line 18 is where we did the call? No, let's double check, right? Okay. Line 18 is in fact the call instruction. So it is doing, all things considered, GDB backtrack is actually doing a pretty good job of keeping track of who is calling whom from where. How do you think backtrack does all this cool stuff?
It looks at the address.
It looks at that. Which address? You're definitely right, but which address is it looking at?
The one on the stack.
It is on the stack, but it's not the address of the stack. It is the return value is what it uses to imply the line number. But how does it track where's the previous call or information about the previous call? Looking at the stack pointer and looking at the return. Okay, wait, hold on a second here. How does it even know where the return address is?
Compares it to the line. It's called
EBP.
EBP, that's right. Okay, the debugger GDB actually makes extensive use of EBP when you're doing something with the call frames. Okay, so in other words, GDB itself, the debugger, not the compiler, the debugger itself also understands the concept of EBP is supposed to point to its own saved value, and 4 bytes above that location is the return address. That is how it figures out that, hey, now I know where the return address is, and based on the return address, I know who called me. And then it can also look up a table and find out which line number and which file is corresponding to that location. That is how it can figure out that it is called from function f, and it is on line 18 of f.s. All of that stuff comes from the use of the frame pointer, or the correct use of the frame pointer. Yep.
So you can screw with GDB by putting random data into EBP?
Yes. Yes, absolutely. But okay, that will give us one way to go back to the previous call. Okay, how does it go from here back to here? What do we put on the stack? The first thing we get into a subroutine, what do? We save the frame pointer, right? So when you look at the stack, okay, this is the stack. We have call frames here. So we'll only take a look at 3 call frames. This is where we are at this point. So the stack pointer is, nope, sorry, wrong direction. The stack pointer is right here, and the frame pointer points to usually a location that's a little bit before that, okay? But the important part is, this is always an ODBP. So what the debugger does is to use the register EBP, locate these 4 bytes and say, hey, I know where the previous frame pointer is pointing to. It's pointing to, guess what? Another old EBP, which points back to yet another old EBP, and so on. So for those of you who have taken CISP 430, what is this reminding you of?
Linked list.
A linked list. And that is exactly what it is. And GDB relies on all this stuff in order to show you everything that you can see in backtrack. Yep, go ahead.
So EBP not points to like a first address instead of like a follow each frame?
Say again?
So like EBP follow each frame or just like on the first address or?
No, EBP as a register is only pointing to a saved version of EBP. Okay, that's it. Okay, that's all the instruction does. The rest are convention. Okay, so the convention is EBP should only be used as a frame pointer, and the convention also dictates that the 4 bytes right before that has to be the return address. So that's how it can track, using the return address, it can track where the call is coming from the previous call frame. So this is a convention that is used by most C compilers, not just GCC. The Microsoft C compiler probably does the same thing. All commercial compilers probably do the same thing too. It's a de facto standard of how to pass information from one frame to the next. Are there any questions about this part? Yep.
What would the top of the stack?
The very last one?
Yeah.
I have no idea. I know it will go all the way back to main because main is a regular C function. So main will do exactly the same thing, push its own ODBP on the stack before it does anything else. But the caller of main is not a C subroutine. So GDB would actually stop right there and say, okay, we got into main, I'm done. And it knows it's in main because it is looking at the address, and it uses a table to look it up and say, hey, this is inside the main subroutine. And once I end up in the main subroutine, I know there's no need to go any further unless main itself is recursive.
Yeah, I was wondering about that too.
Well, you can make main recursive, but it's just kind of awkward to do it that way.
I'm just trying to think of how it's structured and how it terminates.
Okay. Does anyone want to see a recursive main that actually does something useful? No?
That has something
You guys are bored? You guys want to see it? Okay, fine. Okay.
You don't want to.
Recursive main.c. Now, in order for main to be recursive and actually do something useful, I'm going to use the usual argc and char cons, char, pointer, argv. Okay, that's a confusing way to look at it. This is probably a little bit easier. Okay. In other words, every time you declare a main subroutine in C and C++, it actually has implicit parameters. These are only 2 of the implicit parameters. There are additional ones too. Because I think the environment variables are also passed to main as a, in the form of argc and argv, count and array. But this is just the command line stuff. Okay, so I'm just going to use this one as an example. And in this case, I will write this subroutine to use standard IO. Include stdio.h. The reason is because I want to print something per recursive call. Okay, so I will say if argc is greater than 0, we'll do the recursive call. Otherwise, we can stop, do nothing here, and return 0 over here. All right. So if argc is greater than 0, it means it has at least one parameter. So I'm going to print it out. So I'll do a printf %s \n. So I can print one argument on each line, and that's just going to be argv bracket 0, the first one, and I don't really care about the rest. And then I call main again here. But this time I'll call it with argc -1 because I just took care of one, and the next invocation will pick up the next one, like so. That's all regular C code that you have seen before. You just haven't seen it in the context used in main. Okay, does everybody see what I'm doing here? I'm decrementing the argument count by 1, and I'm increasing the pointer by 1 as well. So I'm taking care of the first element of the array, and I'll call main again and say, hey, you take care of the rest. Well, guess what? I made, so when I call main, I'm getting argc, but this time it's 1 fewer than before, and the address of the array has moved up by 1 element. So my first element now, being the second invocation of main, is actually the second element from the perspective of the first invocation of main. And I'll keep going like this until eventually, there comes an invocation where argc is 0, because every time I do the recursive call, it is subtracting by 1, right? So eventually it gets to 0. When it does get to 0, argc is greater than 0, it's going to fail, it will turn false. I go to the else here, there's nothing to do in else, return 0, go back to the previous one, go back to the previous, like that. So that's how it works. Are we doing okay so far in the concept? All right. Well, let's take a look to see whether this works or not. GCC dash, well, I'm just going to do a -o here because I'm fairly sure this is going to work. And I'll give it a whole bunch of gibberish, like -x, yada yada yada, -o, blah blah blah, -o, -c, blah blah blah. And this is what the program does. It shows the actual arguments on the command line to the executable. That's what argc and argv are for. Do you guys talk about that in your other classes? No? Okay, so you guys learned something new today. Most of the time, we do not process the arguments and switches like these recursively. I'm just using the recursion as an example. Are there any questions? Quick question. How do I print all of these things in reverse order? Exactly. This is why we love recursion. Because changing the order, reversing the order is easy. That will reverse the order because it will do the recursive call first, and when it comes back, it's going to print its own element. So this will print everything in reverse order. So let's do GCC, rerun it, and you can see how it is just reversing the entire order. It will print the last one first. Okay. Are there any questions about recursion in general? Or how to do it in assembly? Is a recursive subroutine any different from a non-recursive subroutine? From the perspective of just how to do the call, how to do the return, how to access the parameters, the local variables, and stuff like that. There's absolutely no difference between a recursive subroutine and a non-recursive subroutine. If we just kind of take a moment here, is this helping to clarify concepts that you have learned in other classes, particularly things that you have learned about recursion? Or have you always known that, oh, I know exactly how recursion is done at a low level, at a lower level? Yeah. Well, I'm hoping this is going to be helpful because, without looking at this, sometimes people look at recursion like, it's some kind of magic, but it really is not magical. Okay, the most difficult part is to understand there's one set of variables and parameters per invocation, not on a per function basis, but on a per invocation basis. Is that okay? Well, if that is okay, let's move on and talk about something else. Yep, go ahead.
The file name is also part of it?
Yep. That's why you can know, you can always know, how you are invoked. As a program, you know how you are invoked. Which is handy sometimes. You can basically know which folder you're in. Now, in this case, you only know that it's a dot, which is the working directory, the current working directory. But you can use a system call to find out what is the current working directory. Then you have the full path of the current working directory, so you know exactly where the executable is. Right. If there are no questions about this, let's go back to my notes and kind of take a quick look at where we are in terms of the notes. So we have talked about the stack, using the stack in assembly language programming, the push and the pop instructions. We talked about call and return. We talked about the make program. We talked about the call frame, local variables, return value. We talked about parameters. We talked about register use in functions. No, I'm not quite sure what it is. Oh, okay. This is actually a duplicate of the call convention here. Did anyone bother to click on these links on Moodle? Okay, I certainly hope that you guys understand that it's here for a reason. I want you guys to read it. Okay, so these two are basically somewhat duplicates of each other. C calling convention, basically says you can use EAX, ECX, and EDX to your heart's content from the perspective of a callee. You do not have to save and restore those registers. But if you use EBX, you better save and restore it, because the caller is counting on the callee to save and restore EBX. And this is also one of the most common problems with assembly language programming, is people start to use all the registers, including EBX, and not remembering to save and restore EBX. And then the caller will see EBX being changed, and everything will fall apart. So if you need to use EBX in a subroutine, you need to save and restore the value of EBX. Make sure that from the perspective of the caller, EBX is not changed. All right, so let's see, that's it. I mean, that is really all the topics under subroutines. And all of the links are corresponding to all of these topics here, and they're all in the curriculum of this particular course. Are there any questions? Well, let's see how we can mess up programs then. Now that we have a pretty good idea of how the stack is being used, how the frame pointer works, how the return address works, and stuff like that, let's try to mess up some C programs, but only using C code, okay? And we'll take a look at the symptoms of those particular things, okay? So we'll start off with something that is a little bit easy. And I think I might have an example from the beginning of this class. Did I show you an example where weird things happen to a program? Yeah. I thought I did, but I'm not 100% sure. It might be.
You provided a link to resources of some things to be debugged.
Okay.
That's one, yeah, first one.
The first one?
Yes. First or second one.
This one?
Yeah.
Yes.
This one is not too bad. it really is not. I'm going to show you something that's worse than this. Okay. Let's talk about this one. I'll give you a clue, okay, of how it is messed up. Okay. We'll start with the usual stuff. And I'm going to have F, a main calls F, and a return 0 right there. Okay. Pretty easy. and then we'll go ahead and write f as a subroutine. As a subroutine is kind of awkward. It has a integer array x with only one element, and now I'm doing the computation of where it can how much offset it needs to go in order to mess up the rest of the program. So because we have two additional things in between, so that would make it 1, 2, 3, 4. Okay, so I'm gonna do something with this one. If you do something like this, the program will just crash really hard as soon as f returns, and you would probably associate the problem with subroutine f. So I'm going to do something that will not make it crash like right away. Instead, it will do something that's really odd. Okay. So I'm going to do something like maybe a minus equal to. I'm kind of guesstimating here because I have to estimate the number of instructions to offset. So I'm gonna give it an 8, which is just an estimate. So this program, if I really wanted to make this work, I kind of have to tweak it a little bit. Okay. In function f, and g doesn't do anything except to announce that I'm in function g now. All right. So this is. It might take me a few tries to get this done, but that's the objective. Okay. That's mysterious for one thing, right? It's calling itself over and over again. There's an infinite loop of some kind in this program. Okay. You present this program to someone who is a veteran C programmer. And that person is going to say, there are no loops here. No, there's a loop here because I can definitely tell from the output it is doing something over and over again. Okay, now you guys obviously know the problem is the array x as a local variable only has one single element. But I try to access the 5th element, which does not exist, right? Well, C doesn't care. C assumes that you are an expert programmer and you know what you're doing. If you want to pretend there are 5 elements in X, sure, we'll assume there are 5 elements in X. Not a problem. Okay? But what you're actually messing around with in this case is the return address. So I mess around with the return address, but how did I mess around with the return address? I made it go back 8 bytes. The return address is supposed to be continuing after the call itself. Now that I rolled back 8 bytes, it's going back to the call to f, or at least it slides down to that point, so it will keep doing that again and again. Okay? But by changing the offset of 8, it can do all kinds of crazy stuff. So let's check whether 16 is enough to do something that is even more crazy. Well, we know it's not crazy because it's just messing around with the stack. Okay, it says in F legal instruction. So it takes a few try because it's. I suppose I can cheat and actually use GDB to find out exactly how much I need to subtract to really mess it up. Should I do that?
Yeah, go ahead.
Okay. So if I cheat to do this, I would have to turn on the debugger or debug option. And GDB return. What I need to do is to put a breakpoint in F. Run the program, now I'm in F. So what I need to know is what is the current return address on the stack. So I'm going to say print /x, x bracket 4, which is a return address. I'm hoping you guys by now can recognize this is a location where instructions go, right? And then what I'll do is I'm going to say, hey, tell me what is G. Fine. How about that? And then we can do the subtraction. So we can say cast this into an integer and subtract x bracket, yeah, x bracket 4. Maybe, yep, there we go. Okay, minus 46 is what we need. This is going to be fun. Okay, so based on how I inspected the program in GDB, and based on your understanding of what is on the stack, what do you think this time this program is going to do? It will return to G, which is going to be a very strange symptom for someone who does not understand how the stack, return address, and stuff like that works. And trust me, this is not the worst of them yet. Okay, I can mess around with this program in a way that is even worse than what we are seeing here. By corrupting different things, it will give you different symptoms. It says, I'm in function f, and then it's in function g. But someone who's going to read the source code is going to say, but function g is not even called by main in any way. It's not called by main, it's not called by f, so how can we be in function g? Has anyone seen anything like this when you're debugging your C or C++ programs? I have, and that's because it's because I was using an array of integers and I was changing the elements incorrectly and end up with something like this. Now remember what I said, this is not the worst. Let's try to make this program even worse than what it is. So this time we mess around with x bracket 3, and we'll offset it by 4. But to demonstrate this particular problem, I'm going to have to use extra variables. So we'll have 3 variables, and we'll go ahead and initialize x to 23. And you can actually do this, comma is a valid operator, y to 14, and z to 64, and do the initialization before f. And at this point, I'm going to do some inspection and see, how those values are coming along. Okay. Put a breakpoint on line 18. Run the program. Now we are on line 18. So we go into the subroutine. Print f, do this kind of nonsense thing, return from the subroutine, and guess what? It doesn't have a problem getting back to main because I did not mess up the return address. What I did mess up is the thing that has a lower address than the return address. What is having a lower address than the return address? This is the return address. What is right below it? It's the old EBP. I messed up the old EBP. So the frame of main is now misaligned by 4 bytes. Now when that happens, really bad things will happen when you look at the local variables. So let's check out our 3 local variables. What were they supposed to be?
23, 14, 64.
Let's take a look at the program. So they're supposed to be 23, 14, and 64, and now x is 14 instead of 23, y is 64 instead of 14, and z is 1 instead of 64. That's because the frame pointer is now misaligned. And all the variables got shifted by 4 bytes. Okay? Now, when you're only looking at the C code, can you explain, what is happening with this program other than, hey, array X only has 1 element, you're accessing the 4th one, and that's not a good thing to do. Now, if you go back and look at the program, you might think, hey, this is something that Tech is just using to demonstrate concepts in the assembly language programming class. In real life, nobody is going to do something like this. Yep.
Can we check with a backtrack here?
With backtrack, after we mess around, backtrack will still be able to backtrack, but it will still be able to backtrack back to main. But when you do the frame thing, it will also display the wrong information because it's still relying on the messed up EBP that is saved on the stack. Okay, getting back to what I was talking about. Oh, so when you look at this program, you can kind of easily pinpoint and say, hey, this is just really a made-up program to intentionally make it fail in a certain way. Well, that's only because this program has only how many lines? But maybe 20 lines or so, okay, when you display the whole thing. What if your subroutine F is not 3 lines long? Instead, it has loops and conditional statements and all kinds of crazy stuff that is changed in the index that is indexing into X. What if you pass the address of X to another subroutine that will do some computations? That other subroutine would not have any idea of what is the actual length of the array, but it will still end up with the same result of changing the frame pointer, in this case, on the stack, or the return address on the stack. But because of that, the program will fail. It's just that in real life, these problems are even much harder to spot because it's not spelled out like this. You guys saw, how I did it and go like, yeah, it has to do with that line. Even if I cannot explain why, I know which line is responsible for the symptoms. But in real life, those lines will not stand out at all because all you will see is X bracket I, using a variable or an expression, and it's going to change the value of that integer. And the worst problem of something like this is worse than the one before because the crash did not happen, or the mysterious stuff does not happen right after F returns. Well, it doesn't happen in F. Okay, that's bad enough. Okay, it happens only after you return, and the symptom is not crashing either. So unless you're shifting a pointer so that the pointer is no longer valid, it just gives you like totally crazy values in the variables. Yep.
So how are we gonna debug these kind of problems?
How do you
debug that kind of issues?
I think there's an option in GCC. You can actually put in extra code that will slow down the execution of your program, but it will do some sanity check to make sure that your program or the stack frame is still intact. So it will push some extra bytes on the stack, kind of like checksums and whatnot, and it will also emit additional code during the entry code and the exit code. It will emit extra code to double check the checksums and all the other stuff that it intentionally put on the stack is at the right place. So I cannot remember the option. You can probably look it up pretty easily. So GCC stack sanity check. Okay, sanity checking package for GCC stack overflow build sanity check. So there are ways to do it. You just have to kind of look it up. But it will slow down your program. So you only want to turn on these things while you are debugging and making sure your program is right. When you are in production, the production version of the executable probably should have these things turned off, because otherwise you will suffer a performance penalty because of it. Are there any other questions about today's lecture? All the fun stuff you can do in C. No. No one seems to believe that you will ever run into something like this in your career as a developer.
Sure.
Now, I think most people are just thinking, I'm just going to avoid C and C++ altogether. Python and Ruby on Rails, here I come. From here on, I would only deal with interpreted languages, no compiled languages for me. Which actually you may be able to get away with in these days.
Still break things. You can still break things in any language.
Yeah, but the other languages would not allow you to do something like that. Okay,
Yeah.
The ability to do pointer arithmetics and access any location with a dereference operator are the culprit of most of the problems with C and C++ programming. Well, not counting memory leaking, that sort of thing.
Yeah, it really sucks.
All right. No questions? Okay. To me, as far as I'm concerned, this is the value of this class. I know that most of you will not program in assembly ever in your career. Okay, that part is, I know for sure. But C and C++ programming, I think most people cannot avoid it. This gives you some additional ideas. When your program behaves really strangely that you cannot explain, you can now start to suspect the stack is corrupted. Okay, just knowing that the stack being corrupted will lead to all kinds of crazy stuff like this gives you some additional information. Instead of looking, all over the program, you now will know, hey, I'm going to look for, accessing an array out of bound, because that is the primary reason why you can corrupt your stack. All right. So I'm done with today's lecture. There are no structured activities, during the lab time. You can do your homework, and I will be there to answer questions. For those of you who want to explore today's topics further, we can use the lab time to kind of play with more C programs and find more ways to crash them.
Any idea about midterm grades?
In progress. Yes.
I don't want to know.